Okay, so yeah, this is the part that matters most. So here we are. I've started a new recording just to make it clear for the people that didn't quite make it to Hangouts and aren't listening in. But in any case, when you have something going in a circle, and this is showing it here, this picture here of going in a circle is pretty nice. The problem is the acceleration's not changing in its amplitude, which it would do in a vertical circle. So this is actually meant to be a horizontal circle here where you're not changing. The reason that it changes in a vertical circle is at the top, gravity's pulling down, which is what you want for centripetal. It's pulling it towards the center. So mg and the normal force are both pulling downward, which is helping the centripetal force occur. Remember that centripetal force is always the net force. And so when you're at the top of an upside down loop-de-loop, the normal force down and the gravity force down are working together, and your net force is the sum of those two things. Instead, at the bottom, it's much different because the normal force is now pushing up. And by the way, if you're not on an upside down loop-de-loop, but if instead you're, say, a weight that's being swung on a rope, then it's the same thing. At the top, the string's pulling down and gravity's pulling down, so they're working together to create the centripetal force. But at the bottom, they're fighting each other because gravity's pulling down, but the string's pulling up. Or in this picture, gravity's pulling down, but the normal force of the roller coaster's pushing up. And so on the bottom, you can see the normal force ends up needing to be much bigger. Because it has to counteract gravity and then be bigger to have some leftover force for the centripetal force. Okay, and if you're looking at, say, a roller coaster, which is the third problem I want to do today, it's kind of tricky because at the top, at D here, when you're going around an upside down loop-de-loop, at that point, you've got the normal force pushing downward and gravity pushing downward, so you have two things that are helping you to create that centripetal force, remembering that the centripetal force is always the net force. At B here, at B, the normal force is pushing up, which is going to help make some centripetal force, but it's got to do more than that because it also has to counteract gravity because gravity is pulling down, which is the wrong direction. Because the cart, as it comes around B, is kind of going in a circle at that moment. And so you have a centripetal force upward that has to be there. It has to be a net force. And so the normal force will be bigger than gravity at B. The normal force has to be bigger than gravity. At C, sorry, I'm going to get through this, then I'm going to stop the video. At C, what happens is we need a downward force, and gravity might not be big enough to make a circle because C, it's also going in a circle at that moment if you think about the top of the track. And if you've been on a roller coaster, when you get to C, that's when you come shooting out of your seat, right? This is when, if you don't have the seatbelt on, you're going to die because as the roller coaster goes over the top of the hill, you go flying off into space. And so you need to have your seatbelt on because the normal force actually has to pull downward. And then if you look at the tracks on roller coasters, they like have grips on them so that it's not just push. The normal force can push either direction, right? So in any case, at C, we need to force towards the center, and gravity might or might not be big enough to do that. And so you may still feel normal force upwards or not, or maybe you'll feel like you're in free fall. Depending on the forces involved. But the key to all of these is that the net force, which is typically just the combination of gravity and the normal force. So you add your gravity force, you add your normal force as vectors, I mean adding, which means sometimes you subtract them if they're in different directions. But you combine those two vectors, the one for normal force and the one for gravity, and that gives you your net force. And so the normal force might not be the same as gravity. In fact, it can't be if you're going to be going in a circle. And so the leftover force, the net force, has to be equal to mv squared over r. Okay? And we get V often by using potential energy versus kinetic energy issues. So there's 5 minutes of me saying everything that was really important. I'm going to stop the recording and put it on YouTube